First objective is to appreciate the unique metabolic demands of skeletal muscle and how those demands change for different types of skeletal muscle. We're going to look at some of the different fiber types that will have different metabolic demands. We're going to skip and eliminate objective 2. We usually don't have enough time to cover this, but we will again shift to objective 3 as we start module 4. So this objective will be our last objective for module 3. So when you think about skeletal muscle metabolism, this is really how do muscles get their ATP? What is their major source for ATP? And if you think way back to the beginning of the semester when we spoke about the cellular respiration, the different means of making ATP, we spoke about some means that used oxygen, such as oxidative phosphorylation. This is what made the most amount of ATP. But we also looked at the glycolytic pathways, which happen as far as glycolysis, which generates a smaller amount of ATP. So there can be different means of making ATP, and that's how we can classify different types of muscle by their major source. Now, ATP is required. It's absolutely essential to power contractions. Contractions are going to rely on calcium, as well as the ATP binding to the myosin head, which is what energizes it to carry out the power stroke. So ATP is absolutely essential for contractions to happen. Now, the ATP is going to also determine the strength of those contractions, the speed of those contractions, and so that is also going to help us classify muscle based upon their fiber types, if they're fast muscles versus slow muscles, by the speed of their ATPase. Now, the sources that we can get ATP from, here are some of those. Again, this goes back to our discussion in cellular respiration, chapter 3. So the sources we want to think about are phosphorylation by creatine phosphate, and that is a temporary sort of transient source of ATP. So this is basically on tap, waiting for the next contraction. So this is a temporary source of making a very small amount of ATP just to get the contraction started. The other two sustainable sources are oxidative phosphorylation. This happens in the mitochondria. This is where we make the most amount of ATP across the inner mitochondrial membrane. This is reliant on oxygen. So what we're going to see is that muscle activities and the types of exercises that rely on oxidative phosphorylation, we're going to need to have a steady supply of oxygen. So there's going to need to be keeping up with the supply of oxygen in terms of keeping the breathing rate, keeping the respiratory rate at a feasible level. And then the third mechanism here is anaerobic glycolysis. So this is going to be what gives us a smaller amount of ATP. This is substrate level phosphorylation. And so this is only going to be able to give us ATP, but there's going to be a price to pay that we speak about. There's going to be pretty much lactic acid buildup as a byproduct of that, as you can see here. But this can be done in the absence of oxygen. So this is going to power stronger contractions. This is going to power activities like sprinting, where you can't necessarily keep your oxygen flow steady, but you can generate a lot of ATP, not a lot of ATP, but a more sustainable ATP in the absence of oxygen. Okay, so that is the difference between the mechanisms of muscle contraction. Let's look at the first one. Again, that temporary one, it's the creatine phosphate system. And this creates a small store of ATP while the muscle is at rest. And this is to allow the muscle contraction to start quickly. So because muscles should be very responsive, right? When you think to move your arms, think to lift a heavy load, that should happen pretty quickly. And there's not enough time for ATP to be made on demand. So the creatine phosphate system is what keeps a small store of ATP ready to go on tap to start the contraction. And then the other mechanisms can take over because they'll have more time to sort of get warmed up, right? The machinery can get warmed up to make those other sources of ATP. Now, the reaction here is creatine phosphate on one end and ADP. And then with the enzyme creatine kinase, we can take the phosphate from creatine phosphate, add it to ADP on the other side of our equation here, and that is how we phosphorylate ADP to make ATP. Okay, So this is, again, a small amount, transient, about 5 times the quantity of ATP that is at rest. So it can give enough to just get this contraction going. And then the law of mass action applies to this reaction. So if we have a lot of ATP on this side, we will drive the reaction to the left. That is, we will make more ADP and creatine phosphate in the opposite direction. That is if we have enough ATP already existing on tap or on demand. If we had the opposite, let's say we had a lot of ADP, we would drive the reaction towards the right. So we can actually phosphorylate that more, make more ATP, and keep that on store to supply the contractions. Now let's look at the other two mechanisms. And in order to do that, we want to think about the types of exercise intensity. So we want to distinguish between light intensity exercise, such as walking, jogging, things like housekeeping, house cleaning, versus heavy intensity activities like jogging, not jogging, but sprinting, heavy weightlifting, those types of more rigorous and vigorous activities. So we're going to begin by looking at the types of metabolic demand, the type of ATP source for light to moderate intensity activity. So because we can usually maintain our respiration during these types of activities, we can rely on oxidative phosphorylation to power these contractions, right? Because we have oxygen coming in via respiration. Initially, we're going to start with glycogen stores. So the body's going to be efficient in this way. It's going to use whatever it has on store. So we're going to tap into any stored glucose, which is in glycogen, convert that to glucose, and use that to power the initial part of the activity. That can last up to 30 minutes. So up to 30 minutes, we can metabolize glucose, fatty acids that are either glycogen or stored in the blood, or circulating rather in the blood. Now, beyond the 30-minute mark, we're going to see oxygen supply being steady. We're going to keep ventilation. That's going to start to increase to bring more oxygen in. Heart rate would also increase to sort of circulate that oxygen throughout the body. And then blood vessels will also dilate to move that oxygen around. So now we're going to be able to sustainably rely on oxidative phosphorylation, okay? We're also going to see a transient increase in the GLUT4 receptors, and the GLUT4 receptors are inserted into the cell membrane and allow the cell to uptake glucose and is able to metabolize that in order to make ATP as well. So there's going to be an uptake in the amount of GLUT4 receptors in the cell membrane so it can use more of that glucose that's circulating in the blood. So looking at the illustration here, the graph, we have the energy used per source, the amount of energy for each of these mechanisms, and then the time. Now, as we can see in the initial minutes of the contraction, again, this is light intensity or light to moderate activity. In the initial minutes, we can use creatine phosphate by the creatine phosphate system just to get the contraction started. But notice how that slowly tapers off, while the other two mechanisms are going to start picking up. So the second mechanism that is going to last for about 30 minutes or so is going to be anaerobic glycolysis. And we're going to tap into any stores, tap into any circulating glucose, any circulating fatty acids, and use those up for the first 30 minutes. Beyond that 30-minute mark, oxidative phosphorylation is going to take over as the main supply of ATP. And the reasons that I mentioned is because ventilation is increasing to bring in more oxygen, heart rate and the contractility of muscles and the heart increase to circulate that oxygen, and then blood vessels dilate also to help circulate that oxygen. Let's shift to think about heavy intensity activities. Examples here again, sprinting, as I mentioned, maybe martial arts, very combat type sports, soccer maybe. And so these types of activities are going to limit the respiration, limit the ventilation. And so here, we're not going to be able to rely as much on oxidative phosphorylation just because we can't usually maintain the oxygen flow in these activities. So the caveat here is with anaerobic glycolysis, we're going to have lactate build up as a byproduct. Pyruvate, which is the end of glycolysis, because it can't be shuttled into oxidative phosphorylation, it's going to build up and it's going to be shuttled into lactic acid, and that lactate will build up. And that will actually cause the burn that we feel in the muscles with those types of activities. So when you're, lifting heavy weights, after a couple seconds, really to minutes, you're going to start feeling that burn in your muscle. And that is the price to pay of using anaerobic glycolysis in the absence of oxygen. Now, after you have finished that activity, your lactate will clear and then that burn will go away. And then you'll go back to sort of relying on oxidative phosphorylation as you can maintain your ventilation at that point. Now, this is only going to give a small amount of ATP, so 2 ATP per glucose. But it's going to be enough to power those contractions pretty much because of the fiber types that are associated with anaerobic glycolysis. We'll speak about how those fiber types are conditioned to rely on anaerobic glycolysis, and they have certain features that make this more favorable, such as in bodybuilders, and we'll look at those examples. Now, the illustration here is a little bit different. We start with creatine phosphate. This is the same, but after that initial powering of the contraction just to get it started, we're now going to shift to relying on anaerobic glycolysis. This goes way up. And so the rate of respiration here is not enough to sustain oxidative phosphorylation, but it doesn't disappear, right? It's not entirely zero. There's still going to be some amount of oxidative phosphorylation happening, but it's going to match whatever amount of oxygen you can supply, which is not as much during these types of activities. Okay. Now, on that basis, we can think about distinguishing different types of skeletal muscle. This is how we can classify skeletal muscle fibers based upon two things. Their velocity of contraction, we can describe them as being fast or slow, and their primary source of energy, and we can describe them as being oxidative versus glycolytic. So we have these two ends of the spectrum, fast versus slow, and then we have, in terms of the power source, oxidative versus glycolytic. Now, we also have somewhat of a medium when it comes to the energy source. So with the energy source, we also have somewhat of a gradient in the middle where we have the two ends of the spectrum, oxidative, glycolytic, and then we have somewhat of an intermediary in the middle. So the difference in speed is fast twitch versus slow twitch fibers. And this is based upon a few different characteristics of the muscle. So one will be its myosin ATPase activity. This is how fast it can hydrolyze that ATP. So we talked about how the myosin binds ATP and it goes from its high energy form to low energy form, where it's now ready to power the cross-bridge cycle. So if that ATP can be hydrolyzed very quickly, then it can actually power the contraction faster. So a faster ATPase rate equals a faster cross-bridge cycling rate, right? So that this muscle would be labeled as fast. So there we can see fast fibers, which have a fast ATPase activity, versus slow fibers, which have a slow ATPase activity, in that the time it takes to hydrolyze that ATP is going to take longer than we see with fast fibers. Now, the other distinction between fast and slow fibers is the calcium ATPase rate. So the calcium ATPase rate means that the muscle can now relax faster. Remember, calcium ATPase is the enzyme that pumps the calcium back into the SR, which helps the muscle to cease the contraction when that calcium is no longer binding to troponin, right? It's going to cover up the binding sites and the muscle can go back to being relaxed. So the faster the muscle can relax, the faster it can start the next contraction. So that will also constitute a fast fiber. Now, when we compare fast fibers to slow fibers, fast fibers can contract 2 to 3 times faster than slow fibers, which simply means that in the time it takes a slow fiber to power one contraction, a fast fiber can power 2 to 3 contractions in that same span. What it also means is that the duration of the contraction is longer with slow fibers. So slow fibers are going to contract for a longer duration. And so that is going to be seen in different types of muscles that are going to be needed for longer types of activities like the types of muscle that are associated with our posture, all right? Versus the types of muscles that are associated with quick, delicate movements, like the movements of the eyes and the movements of the fingers. So just to give some examples here. So here we're comparing the tension, and that is the percent of maximum force generated by each of these muscles versus the time. And this is in response to a single stimulus in terms of the motor end plate. Now, what we can see is that a fast muscle would be the extraocular muscles. They can start their contraction faster and their contraction faster, which means that they can hydrolyze ATP faster and they can relax faster by their calcium ATPase activity. The types of activities that we see here are the extraocular muscles. So this would be muscles that help us to do the quick movements of the eyes that should be really fast and responsive versus the gastrocnemius muscle. So the gastrocnemius is going to, in response to a single muscle contraction, it will take a longer time to reach its maximum peak or its maximum tension produced. And then it's also going to take a longer time to get to its fully relaxed state. The gastrocnemic muscle is going to be one of our calf muscles. So that's going to be one of the powerful muscles that help us to walk and run and jump and sprint and all those good stuff versus the soleus muscle. Now, the soleus muscle is also a calf muscle, but it's a deeper muscle. And as we can see, it takes an even longer time to get to its maximum tension produced, and then a longer time to get to its relaxed state. And you can see this is much longer compared to the other two types of muscle. So this means that the soleus muscle, being a deeper leg or calf muscle, is responsible for posture. This is what allows you to stand for hours on end, to walk for hours on end, right? This muscle is always contracting. Its contractions last for a longer period of time versus the gastrocnemius, which is really involved in quick actions, in powerful actions that are going to be sort of on demand, but then relax really quickly. Now let's look at the different fiber types and look at their different features and their ATP production, their main source of ATP production. Now I want to give a little bit of a disclaimer. While we speak about glycolytic fibers versus oxidative fibers, I want you to remember that muscle fibers are usually mixed. So we're not going to find all of one type and none of the other. We're going to find a mix, but we're going to find predominantly one type versus the other, right? And that is going to be dependent on the type of activities that the person is used to. So let's say we have a long distance runner, right? One of those runners in the Olympics that can run for, many miles, long distance, slow running. Their muscles are going to be more conditioned to have more oxidative fibers. That is not to say that their muscles will not have any glycolytic, but it's going to be predominantly more oxidative. Compare that to a bodybuilder. Bodybuilders have big muscles, powerful contractions. They're going to be having more predominance of glycolytic fibers, which can power quickly, but also relax quickly. And so we're going to see mainly and mostly mainly glycolytic fibers, but we're also going to see a little bit of oxidative sprinkled throughout. Okay, so let's begin with the glycolytic fibers first. These are mainly suited for anaerobic glycolysis, and because of that, they have fewer mitochondria. And if you think back to anaerobic glycolysis, it isn't reliant on mitochondria. It's reliant on, it happens in the cytoplasm, so it's not going to be necessarily requiring lots of mitochondria. And so these types of fibers will have less mitochondria. They're going to have many glycolytic enzymes on the other end to help power glycolysis. And they're going to have lots of glycogen stores to be able to tap into that and turn that into glucose to power glycolysis. They're going to use little oxygen, right? This is anaerobic because they don't need oxygen, which is also why they don't need mitochondria or myoglobin. And then they're going to have a large diameter, and then they're going to be quick to fatigue. Now, the large diameter means that there's less of a barrier. We're going to see that oxidative fibers need a small diameter because they need to be able to diffuse that oxygen from the capillaries and bring it into the cell. But the large glycolytic fibers do not need that diffusion, so they can have a thicker diameter. But because of the lactic acid, remember that price to pay with anaerobic glycolysis is the buildup of lactic acid. And because of that, these types of muscles are going to be very quick to fatigue. So they can quickly generate a lot of force, but they'll also very quickly fatigue. And we see this with bodybuilders. Bodybuilders usually cannot run a marathon, right? They have a low fatigue threshold. They are strong, right? They're strong in terms of the power that they can generate, but the stamina, right? The ability to power those contractions for a long duration is seen more with long distance runners who have more oxidative fibers. Okay, so the features here with glycolytic fibers, anaerobic glycolysis, little mitochondria, fast, powerful contractions, and the fibers here are thicker in their diameter. We also want to think about how they stain differently in terms of the histology here. So because they don't have a lot of myoglobin, which is what we see in terms of the storage and the mitochondria, we are going to see that they appear white, and we call these white fibers or glycolytic fibers, versus the darker staining fibers, we're going to call those red fibers or oxidative fibers. And notice how they also have a smaller diameter, and they also have lots of capillaries to bring that oxygen in because they're reliant on oxygen. So looking more at the oxidative fibers on the other end, they rely on oxidative phosphorylation. They have lots of mitochondria because they need that to make ATP via oxidative phosphorylation. They have lots of myoglobin, which is the storage form of ATP in these muscles with lots of mitochondria. They also have a smaller diameter so that they have a smaller diffusion barrier for that oxygen to move from the capillaries into the tissue. And then they're going to be resistant to fatigue. They're going to be able to power contractions for a much longer duration of time, right? Again, think back to your long distance runner.